Hey everyone, and welcome back to The Explainer. Today we're doing something a little different. We're taking math right off the whiteboard and showing you how it literally builds the physical world around you. We're diving straight into Chapter 7 of our source material today, and the whole thing is focused on one specific shape. Well, actually it's more of a specific fundamental corner that completely dominates the structures we live in, work in, and rely on every single day. So, what is it? And why on earth has human engineering been so completely obsessed with this one specific geometric relationship for thousands of years? Let's unpack the mystery behind the hidden structural anchor that silently holds up our modern world.
Have you ever just sat there, looked up at the ceiling, and thought about all the invisible forces at play keeping it up there? I want you to take a brief second and actually look around the room you're sitting in right now. Check out the corners, the windows, the doorways. Today, we're going to train your eyes to spot the invisible geometry holding all of that together. It's this incredibly complex structural math hiding right in plain sight, basically masquerading as simple, empty space. We are so used to it that we take its stability entirely for granted. But let me tell you, once you truly see it and understand the physical tension it relies on, you absolutely cannot unsee it.
Section 1. Angles in the real world. Everyday geometry.
Before we get bogged down in formal definitions and mathematical rules, let's just start by hunting for angles out in their natural habitat. Think of a standard analog clock. That opening between the minute hand and the hour hand, it doesn't just tell you the time. It creates this dynamic, shifting angle that changes every single second, carving a circle up into precise, functional slices. Or picture the two aerials of a classic TV antenna stretching up into the sky. The angle they're positioned at isn't just random. It is carefully calibrated to intercept invisible radio waves and optimize the signal. And what about the heavy wood beams making up a pitched roof? The precise angle of that pitch dictates how well the roof sheds heavy rain or snow, which literally determines if the house below stays safe and dry. So whether it's keeping time, tuning into frequencies, or protecting a family from the elements, angles are highly functional, everyday tools.
Okay, let's get a little hands-on to understand how these actually work mechanically. Because geometry isn't just numbers on a page, right? It's physical tension, rotation, and structure. If you grab a simple, fresh, green eichel, a flexible, pliable twig, and you bend it right in the center without snapping it, you can lay it completely flat on a table. Pin one half down firmly with your hand, and then slowly rotate the free half across the table. When you do that, you are physically creating an angle right in your own hands. You're feeling the pivot. As you move that free end, you can literally watch the space between the two halves open and close. That is the very definition of an angle, the amount of measurable turn between two straight lines sharing a common endpoint.
Section 2. Creating your own angles, a DIY geometry lab.
Now that we know what an angle physically feels like, let's head into our DIY geometry lab to engineer a very specific, foundational type of angle. We're going to make it using just a blank piece of paper. Imagine taking a perfectly round piece of paper, a circle, which represents this continuous, infinite curvature without a single hard edge. Fold that circle exactly in half so you get a semicircle. Now, without opening it up, fold it in half one more time, making sure those outer edges line up perfectly. Press down firmly, get a really sharp crease. Finally, unfold the whole thing, lay it flat, grab a ruler and a dark pencil, and trace right down those straight, intersecting fold lines in the middle. We're essentially taking something boundless and structuring it into something rigid and defined.
Look at this geometric transformation. By taking that pink circular piece of paper and folding it down, you are left with a perfect quarter segment. You've taken a continuous, perfectly round curve, and with just two simple, precise folds, you've engineered a sharp, mathematically exact corner. The edge of that quarter segment is a total departure from the endless sweep of the circle. It gives us a defined, structurally rigid point of intersection. It's basically the physical manifestation of turning a fluid, abstract concept into a reliable building block.
Section 3. Defining the right angle, the absolute foundation.
All right, so here is the big aha moment. When a circle is divided into 4 equal parts by 2 straight crossing lines, just like those dark fold lines you traced, each of those 4 equal angles is exactly one right angle. That simple, sharp corner you just engineered by folding your paper into 4 equal pieces is the absolute foundation of structural geometry, the mighty right angle. But why is this specific 90-degree division so incredibly important? One word: gravity. The right angle is simply the most efficient, stable way to transfer weight straight down to the earth.
If the walls of your house or the steel beams of a skyscraper are off by even a single degree, say 89 degrees or 91 degrees, the entire structural integrity is totally compromised. Over time, gravity exploits that tiny imperfection, causing the structure to lean, fracture, and eventually fail. The right angle is quite literally the uncompromising anchor of human architecture.
But, identifying these anchors out in the wild can sometimes be a bit tricky. Notice how the right angle stays exactly the same, whether it's sitting flat and upright like the hands of a clock striking exactly 3 o'clock, or if it's tilted dynamically on a diagonal diamond grid. The orientation changes, sure, but that sharp, perfect 90-degree division remains exactly the same. Our brains try to trick us, right? We're just so used to seeing right angles perfectly aligned with the horizon that when the whole system is rotated, our eyes instantly perceive it as a skewed shape. But math doesn't care about perception. The structural integrity of that perfect quarter turn remains resolute, no matter how it sits in space.
So now that you know how to build one, what it looks like mathematically, and how it behaves even when it's tilted entirely on its side, I'm going to challenge you once more. Look around your environment. Can you spot exactly 3 right angles in the room you are sitting in right now? Where did the builders hide them in plain sight to keep your ceiling up? But let's take it a step further. Imagine what this room, what your house, or what our sprawling modern cities would actually look like without them. If the right angle didn't exist, our structures would quite literally collapse into chaos. Human civilization, in all its towering glory, is essentially built on this one single, mathematically perfect, reproducible fold. So take a look around, appreciate the hidden math holding up your world, and we will see you in the next explainer.